All right, and now that the lecture is recording, welcome to class today. I wanted to give a quick reminder that this weekend is our first exam. It will open essentially just after midnight tonight, so it'll be open all day Friday from 12 a.m. and then all day Saturday, and it closes just before midnight on Saturday. So again, that exam, hopefully you're seeing my screen here, is over chapters 1, 2, and 3. We'll be covering chapter 3 today. We covered chapter 2 on Tuesday, and then chapter 1 we covered last week. So before we get started, I haven't seen any emails about questions on the study guide. Does anyone have any questions right now before we start class on the study guide, about logistics for the exam, or anything like that? All right, I don't see any hands going up. You don't have to type out the whole question. If there's something on the study guide you had a question on, just say like number 5 or something like that would be sufficient, and then I can cover that. But if not, we can jump straight into chapter 3. All right, well, as a reminder, the exams do have a time limit. So make sure that you start the exam well enough before its deadline. So as an example, if you start taking the exam at 11:30 on Saturday, and then you don't finish it until 12:15 or something like that, that last 15 minutes, you will essentially, it'll save your exam at that at midnight. So it's going to save the exam, and anything your screen will still be open, but it won't be saving any of your work at that point. So make sure you start the exam well enough before the deadline that you can finish it in time. All right, I do see a hand from some students. So Brianna, go for it. Looks like you've got a question. Feel free to take the mic.
Yeah, I was just wondering, what is the time limit for the exam?
Good question. It's usually around in between 70 and 90 minutes. So I can go and check right now to tell you the correct time. So you will have 70 minutes. So an hour and 10 minutes to take the exam. And it's about, I can count it really quick. I don't think it's telling me anymore how many questions it actually is. So let's see. I'll actually have to count all the questions. So give me just a second. Oh, wait, no, here we go. It will tell me in this little box. All right, so it's 54 questions and you've got 70 minutes. So again, that won't be quite enough time for you to look up every single question. So do study beforehand, take some notes. Don't forget it is open note and open book. So if there is something that you've forgotten or you're debating between two answers, you can flag that question, come back to it at the end and look that up. That's how I would recommend doing that. So. All right, well, if there's no other questions, let's jump into chapter 3. So today we're going to be talking about sensation and perception. So this builds a lot on our chapter on the brain and neurology. So it's about essentially the receptor cells and how they send their signal and what kind of signals they pick up, how they send that to the brain, and then what we do, how we perceive those things as well. So let's start talking about that. The first thing, hopefully you've read the chapter already, especially since the exam is tomorrow. So hopefully you've read chapter 3 already. Sensation, again, is that getting that information, getting that energy through your eyes, ears, tongue, nose, skin, getting those receptor messages. And then the perception is your interpretation of these things. So there is a sound. What does sound mean? Is that sound a fire truck? Is that sound somebody talking? Is that sound your cat? So what are you seeing? There's the sensation is just the light hitting your retina and the rods and cones there. But what are we seeing is the perception. So are you seeing a color? Are you seeing a pattern, shapes, things like that? So sensation is the sense, the photons are hitting your rods and cones, and so that's the sensation. And then the perception is then what do we do with that? How do we interpret that? So this goes to the idea of bottom-up processing and top-down processing. Bottom-up is the sensory receptors registering that information and then sending that up to our brain. So you can think of it, you get a pain receptor cell on your hand and it's sending a signal. It's sending that bottom up. It's sending that up into your brain. Then top down is our cognitive processes. So now that we have this signal, what is that signal? How do we then interpret it? We tie it into our memories. We tie it into our understanding of what's happening around us in that moment. So that's a top-down process. All right, so as we look at this picture, probably in the chat box, put what you see in this picture. So what is this a picture of? And see if you can describe, like, I see this towards the bottom right, or I see this towards the top left. So describe kind of where in the picture you see something. So let me know what you see in this picture. Thanks for your responses. I'm starting to see them come in. It's always funny waiting for, especially with a longer response like that. Does anybody not see things, or are you just taking a little bit to type? So it's kind of funny to wait. All right, I'll see if there's any other comments. I've got 4 here right now. So it looks like a tree is pretty common. So some people see a tree here in the top left, and then a bush on the right somewhere, and another plant or bush maybe here to the left, a tree growing in this top left corner, a park or sidewalk. So maybe a sidewalk here, and then a tree sitting on a small patch of grass, tree and a tree's shadow. I don't see anything, just black splotches. Very good. That's totally fine, Shay. It's very relevant to our bottom up and top down processing. A face in the bottom, and another tree comment, and black splotches. All right, so I see this tree. I see that tree as well. Here is where I see the trunk. So it's growing straight up there. And then I see either a tree ring around it, or this might be the shadow of the tree to me. An animal is another comment here. I also see an animal. I see a dog right here in this space, a Dalmatian specifically. So the Dalmatian has its head pointed down, so its nose is kind of down here. Here's one of its ears, so its face is pointed, smelling the ground. Here's a shoulder and an arm of the dog. Its body's about right here. Its legs kind of get lost, but I think this is one of the legs. So I see a Dalmatian there. Someone else sees another animal in this general area as well. I see a dividing line. It might be a sidewalk. It might be just different colored grasses, or like grass to dirt or grass to sidewalk. and I also see the black splotches. So how are we picking out things from this picture? Because in reality, it is just black splotches on a white background. So our sensation, what our eyes are picking up, are the light from the white and then the darkness. So we're getting this sensation of light and dark. And then for that, a bear. So someone says they saw a bear there. Brianna, so it could be a bear too. And you might even see other shapes, not necessarily where I was pointing them out too. So our sensation is taking in that light information. Our perception is trying to make patterns out of that. So trying to see, well, is this a pattern? Is this a tree growing over here? Is this a dog? I don't actually have the answer to that. Is this actually a picture? Like, did someone take this picture, put it in black and white, and like turn the change settings? I don't know if this actually ever started out as a picture of an animal and a tree and a sidewalk, but that is pretty similar to what I see. And that's what our perception does. That top-down process takes the information we're getting in and interprets it in some way. So am I correct that there's a dog there, that there's a tree there, that there's a sidewalk? I don't really know. That's my perception of it. Other people's perceptions are slightly different. Some people don't perceive these objects at all, and that is totally fine. One key here is that our brain is programmed to try and find these kinds of patterns, especially visual patterns. And we'll talk about things like the nearness of the black dots, clumping together in groups, and how our mind kind of does that perception process. We do similar kinds of things with sounds. So if you hear sounds in your house at night, especially if you've just watched a scary movie before Halloween, you might think that it was a voice or someone around in the other room, when in reality maybe it was just the house creaking or air turning on, things like that. So our perception tries to put things together based on what we know, based on what's familiar to us. So a park with a dog and a tree, that's fairly familiar to me. So maybe why that's what I see in this one. So that bottom up is getting that stimulus of the light and dark areas, and the top down is putting that together, seeing these patterns. So we've got a couple other funny visual tricks to go through later in this class too. So what are sensory receptors? They are the specific cells. They're a type of cell similar to a neuron, a specific neuron actually, that gets information to send to the brain. So vision, we have rods and cones, and those pick up light energy. Hearing, we have what's called a hair cell, and those actually pick up pressure changes. So mechanical changes, like if it gets touched, essentially. So that's where our hearing comes from, and we'll go into a little more detail on that. Touch is also pressure in a different way. So if something's getting pushed down, this sensory receptor sends a signal. So you can see here, you can kind of imagine, going back to our discussion on chapter 2, this is kind of like the dendrites, or these are kind of like the dendrites. They're the information seeking part of this cell, and then it's got a cell body, and then it has an axon with axon branches to then send that signal somewhere else. Smell and taste are really similar, you can see here. They both work on chemicals. So chemicals affect these cells, and they will respond to chemicals, essentially. All right, so these are the three distinct energies that we can pick up on with our human senses. So photoreception, that's pretty easy to understand, is light. Mechanoreception, that one's mechanical, so things touching one another. And chemoreception is chemicals. So photoreception, here we've got the retina. We'll go in more detail. We don't have to use this picture right now. And mechanoreception, I find it really fascinating that our hearing actually comes from mechanoreception, that it's a mechanical process rather than something else. Oh, no problem, Adam. I'm glad that you're here. I'm glad that you were able to make it. All right, so next we've got chemoreception, and so different cells in the nose and tongue. sense different specific chemicals. And we'll talk a little bit about chemoreception, but mostly about photo and mechanoreception in the eyes and ears today. All right, so for anyone who does ever come late to the classes, as long as I do remember to record them, I am recording this one today. If you've missed more, I mean, we've only missed a little bit right now, but feel free to watch the recordings after. I try to get them onto Canvas basically the next day after the class, but it might be 2 days after or something like that. So check for those. If you don't see it 2 days after, email me, because sometimes I've been known to keep the video private, or like the Canvas block. Students can't actually see it because I forget to click the little green button sometimes to make it public to students. All right, so thinking of the sensory receptors, absolute threshold it's kind of a funny term for this, but absolute threshold is the minimum amount of stimulus energy required to make a sensory receptor fire. So the minimum amount of light energy required for a rod or cone to then fire and send a signal down its axon. So that is the absolute threshold. So you could, I wish it had a different name, like the minimum threshold or something like that, but that's the absolute threshold. You could maybe in your own notes put absolute minimum threshold or something like that. So this is the smallest amount of energy that we can detect as humans. So for sight, it's pretty incredible. On a clear night without pollution and a dark night when there's not like air pollution or light pollution, we should be capable of seeing a candle flame, so a single candle flame, from about 17 miles away. So pretty remarkable. For some of these that come from your book or other places seem kind of silly. Like the touch one is the wing of a bee falling on your cheek from a distance of 1 centimeter. I'm not sure how scientific that one is. I imagine bees' wings weigh different amounts. In addition, your mechanoreceptors for touch in, say, your fingers versus your cheek versus, say, your back, they all have different sensitivity levels too. For taste, we should be able to taste about 1 teaspoon of sugar dissolved into 2 gallons of water. So unless you're my children, then it will take probably 1 gallon of sugar to taste in the 2 gallons of water. So it always seems that way when I'm pouring them like Gatorade or something. They're like, I can't taste it at all. So you just have to keep giving them more and more. And I'm like, nope, that's enough sugar. As for smell, 1 drop of perfume in a 3-room house, which is kind of a funny way to say that. I think cubic feet is kind of what they're breaking that down into, 3-room house. Hearing the ticking of a watch 6 meters away, which I also find kind of funny because some watches tick a little louder than other watches don't tick at all. So the ticking of a watch 6 meters away should be the minimum amount of energy that your hair cells can pick up. With that being said, we'll talk about hearing. There are certain frequencies that humans actually lose the ability to hear as we grow older. So higher frequencies are some of the first lost for humans. So difference threshold. Difference threshold is how much energy is required for a stimulus for us to notice the difference. So a very quiet sound versus a slightly louder quiet sound is going to be a lot easier for us to detect, even if that's like a difference of, let's say, 2 decibels. But the difference between, say, 2 different gunshots might not be detectable. They might actually be many hundreds of decibels louder or quieter, but our ear by itself might not be able to detect that difference. So this is called the difference threshold, or the just noticeable difference in something with very low energy. So low levels of light or low levels of sound. So a whisper or a very dim room. It's really easy to notice someone, say, turning on their phone and having more light in a room, or hearing a whisper and then hearing someone talk at normal volume. You might have experienced that in, say, a theater or something. So that's a lot easier to detect versus if you're in a very bright room and someone turns on their phone, there is now more light in that room, but you might not be able to detect that difference. Like nothing appears brighter to you, even though there is now different light. If you're on a shooting range, someone might be shooting a rifle with a short barrel, making a much louder explosion sound versus a rifle with a long barrel, or maybe a suppressor on it. And depending, well, let's take suppressor out of it. So taking a short barrel rifle versus a long barrel rifle, the short barrel one will be louder. So if you took a decibel meter, compared those two, it might be even a couple hundred decibels, but your ear by itself probably wouldn't detect that. I mean, hopefully you're wearing ear protection anyway, so that makes it even harder to detect that difference. But yep. So that just noticeable difference, that difference threshold, increases with the strength of any stimulus. So as well for chemoreception, if you've got a lot of salt in something, it's really hard to detect one extra shake of salt. But if there's very little salt in something, one shake might seem like a whole lot. So you can detect that little difference when everything's at a low energy. It's harder as it's giving more energy for those receptors. All right, so a big part of our perception, so that was some basics on sensation. A big part of our perception, how we put these things together in patterns, is attention. So attention is just the focusing of our mental resources on any kind of specific information. So it involves a lot of cognitive processing. So with that, we understand and perceive things better when we attend to them. When you pay attention to what your friend is telling you rather than paying attention to something else, whether you're studying or on your phone, when you're paying attention to what they're saying, you will perceive and understand what they're saying better, right? So here's an example. We have selective attention. We have the ability to focus on a specific aspect of an environment, ignoring other things. So that might be focusing on one specific conversation during a party, focusing on one part of a screen during a movie or something like that. So we can selectively attend to things. And we can do that. We can focus on the sweet taste of a dessert. So there might be both sweet and sour. We can focus on other aspects of those that we're getting from our receptors. So this is also called the cocktail party effect, the ability to focus on one thing rather than everything all at once. So why do we choose to attend to things? Well, a lot of this comes from evolution. So we focus on novel stimuli, things that are new, different, unusual, things of a new and different size, things with different colors, things with movement, compared to the environment around us. So with that, because we focus on things that are new and novel and different, we are often not attentive to some things. So this is called inattention blindness. So when we engage and focus our attention on one task, sometimes we miss other tasks around us. Even though our sensory receptors are picking up the information and sending it to our brain, our top-down processing, our perception, we might not even realize that our sensory receptors have received that. So this little video is a good example of that. I think I'm going to open it in not so you can see it and then pull it over here because it might tell you kind of the trick of it. Or maybe I'll just stop sharing my screen. So during this video, it's going to give you some instructions. I want you to try and follow the instructions in this video as best as you can. All right, I have it all prepped. Let's make sure I share my screen. All right, so follow the instructions in the video.
This is an awareness test. How many passes does the team in white make? Go! answer is 13.
All right, so who got 13? Either raise your hand or just say I got it, or if you got close to 13, I guess for everybody, just type in how many passes you think the team in white made. It's all right if you lost count as well. Oh, the video was lagging. Sorry about that. All right, so 11, 12, 8. All right, sorry about that. The lagging video. It's all right. Let's see what else happened in the video that you might have missed.
But did you see the moonwalking bear?
So right over here is a person. Well, can't see my mouse. So over here, a person enters from this side, kind of moonwalks, trying to pause in the middle. So they're behind someone there. So they come in on this side and they kind of walk here. They dance a bit and walk around to this side. So with that, who did see the person in the costume, the moonwalking bear? Looks like Adam may have the first time. Yeah, you've seen this before. Yep, and maybe you've seen other things like this before as well. Did anyone see the person in the costume who has not seen this specific video before? Looks like no, at least no one's commenting that they did see it. So, I mean, part of that might be the lagging video, so sorry about that. But also, this is from inattention blindness. When you're following the instructions and focusing on the passing from the team in white, you're not paying attention to the team wearing black. And so when someone also wearing black, a big bear costume that's black, starts walking through, you don't even pay attention. You are inattentive. Even though your sensory receptors are getting that light data, you're not perceiving that as something that's there in the situation. So this is really relevant to a lot of things in life, such as texting and driving. So let's talk for a little bit about how inattention blindness might be related to something like texting and driving and what that might mean for it. So jump into Teams. It looks like we only have 16 students here. So if you jump into a group and there's already 5 people there, maybe jump into a different one, but jump into the first 3, one of the first 3 groups, either group 1, group 2, group 3. So that's social psych experiments, altruism, pro-social behavior, and personality assessment. So jump into one of those rooms. If there's already 5, if there's already 6 people in a room, jump to the next one. So we'll be back here in this room at about 3:07. So talk about inattention blindness and how sensation and perception might be related to things like driving while texting, intersections, the colors of lights on the cars. So jump into those rooms and be back here at about 3:07. All right, as everybody starts coming back into here, is there anyone who wants to share what they thought up and what they discussed in relation to inattention blindness, texting while driving, other aspects of driving, such as the lights on cars, traffic lights, things like that, and how that might be related to our attention and sensation and perception? Go for it.
So one thing we mentioned in our group was like GPS when we're using our GPS while we're driving, is that sometimes you can miss your turn because you're paying attention more to your phone than you actually are to the road. So it's kind of like one of those like little things that you don't pay attention to anymore.
Yeah, definitely. That actually happened to me just the other day. I was doing a new route to a trail, and I'd never driven on this road before. So there were two turns near each other off of this road, and so I was following the directions. I was looking at my phone, and I turned on the wrong one. I turned on the first one rather than the second one. So yeah, that's a really good example of inattention blindness, that I was focusing my attention so much on one thing that I missed the sensory perception, or the perceptions of what was going on around me. So a good thing there wasn't like a dog running out at that time as well, or probably would have got hit. So any other ideas that your groups talked about? That was a good one that we didn't mention specifically beforehand. So good job talking about that. Go for it. Oh, Kelly, go ahead.
Oh, perfect. We talked about not other scenarios where we get distracted, like when you're talking to someone and texting. And someone made the example that they would actually, when they talk to someone else and they're focused on that conversation, they start texting the conversation towards the person another person that's completely not in the conversation, completely losing what was happening and just texting someone else what was going on at that moment.
Wow, that's a pretty dramatic example. For sure. That's a really good example, though, of inattention blindness, that you're focused on this conversation. And so the other conversation that you're having on text, for me, it just kind of leaves my mind. I can't do the two conversations at once, or try to text, or even try to put like a password in while having a conversation. But that's pretty impressive to be sending live texting the conversation that you're having with someone that's not involved in that conversation. Yeah, really good example. All right, looks like we've got another hand. Was there more that you wanted to say about that, Kelly?
Oh, no, I think I was good.
Yeah, well, good example. And then I see a hand from Shay. Go for it.
Okay, so one time when I was driving, I was first in line at a stoplight, and then I was next to a turning lane. So when the turning lane started to go, I just started to go too, but I was supposed to go straight. And then I almost got in a wreck because the turning lane on the other side was going too. And then I was like, oh, I wasn't supposed to go.
Yeah, definitely. If you're not paying full attention to the task at hand, that's something that can happen if you're just following along with the cars around you. I've seen that happen a lot of times, more times than I wish would happen. So I'm glad you were safe from that situation and you didn't actually get in a wreck, but that must have been really scary. So definitely a good reminder. A funny story related to that, there was a truck following my friend one time that was trying to race him. And so, I mean, my friend driving was being kind of immature about his driving too, and being a little rude with his driving. So the truck pulls up to us, but we're in the turn lane and the truck is in the lane going straight. So the truck was in your position, Shay. So the turn light goes, and so we start going, and the truck really wanted to win the race. So they started going too. They didn't actually get in an accident, and come to think of it, probably wasn't funny for the cars that they did almost get in an accident with. But I did feel a little bit of sense of justice there from, they probably felt quite embarrassed sitting there in the middle of the road through the light cycle. Maybe not a great story to share. It wasn't me driving though. So, but another good example of that inattention blindness. Their attention was totally focused on our car because they were trying to win the race with our car. So they did not pay attention to even what lane that they were getting in, which is not a good way to drive. We need to have a lot more attention there. Pretty big vehicles that can smash people or motorcycles, so definitely be safe while you're driving. Pay attention. There's my public service announcement for today. And I see a question from Adam. How would inattention blindness relate to ADHD? So the way I haven't actually read any research specifically on inattention blindness and ADHD. I know for myself that it can make it harder to focus on that one conversation. So, or if I am very hyper focused on some task, then I tend to have that inattention blindness. But in other cases, when I'm not as directly trying to focus, I do get distracted more easily by the other sensations that are coming at me, whether it be sounds or sights or things like that. So I'm sure it does have some specific relations to ADHD, but I haven't actually read any specific papers on it. So maybe a good topic for a question paper. So we've brought up ADHD in the class, we've brought up inattention blindness. So if that's something that you or anybody else in the class really, it's possible that everybody in the class could write the same 3 topics. I generally have a pretty big variety of topics, but that would be possible. So if anyone wants to do a question paper on inattention blindness and ADHD, feel free. As a reminder, your first question paper is due when our second exam opens up. So it's at the midterm of the class. But you can get started on it earlier. I definitely recommend it. Maybe not tonight when you're studying for this first exam, but as soon as you're done with that, not a bad idea. All right, so with attention, some other things that can happen to us as humans in our brains cognitively is that we can adapt to our senses. So sensory adaptation is a change in the responsiveness of the sensory system based on the level of environmental stimulation. So as an example, you might come into a really dark room and then your rods and cones, they become more sensitive to the low levels of light in that room. If you're right now, probably most of you are sitting. So right now you have a sensory receptor on probably your backside and from the chair and also from your clothes hanging on your body. But you probably don't register that. You've become adapted to that environmental stimulation from sitting on a chair or having clothes on. And now that I'm mentioning it, you might be going, oh yeah, my collar is a little uncomfortable. That's literally what I just thought. But if I'm not calling attention to it, your senses have adapted to that pretty constant pressure of you sitting on a chair or your clothes hanging on you. So unless something changes, like say your clothes get caught on a button on the couch or something like that, and the sense actually changes, your attention will probably not be brought to that. This is also related to adjusting to the hot or cold water. If you've ever gotten to a hot tub, you've probably felt like, oh my goodness, this is really, really warm. But then after a few minutes, it doesn't feel as warm. Similar with cold. All right, so let's dive into light and how we sense light. So light is a form of electromagnetic energy, and it can be described as waves. So we'll talk about wavelengths, amplitude, and the purity of the light. So wavelength is the distance between the peaks and troughs of that wave. So with that, we perceive that through our sensation and perception as color. So different wavelengths are different colors. So the black lights that I just got for Halloween are a much higher wavelength, higher frequency wavelength, and I can see a little bit of the purple light from those, versus red from this bear is a much wider wavelength, and I perceive that as red. So amplitude is related to the height of the wave. And we perceive this as brightness. So you could think of it as the strength of that light, so how bright that light is. And then purity is the how pure that wavelength is. Is it more mixed that leads to a wave kind of like this one, or is it pretty clear and just one specific wavelength? So with that, if there's a mix of wavelengths, we perceive this as the saturation or richness of the color. So if it's just one specific color, we'll see that as a really clear, not very muddy or not very gray, clear blue, for example, in this picture. So humans, we can see the visible light spectrum. This is why we call it the visible light spectrum, because it's what we have visible to us. So it goes way down here from, this is the wavelength, the literal distance between the waves. So 750 nanometers all the way to 400 nanometers. So these waves are a lot closer together here at the blue and violet end of the spectrum than towards the red end. They're much longer wavelengths between the peaks of those waves. So we can see this. Lots of birds can see past this ultraviolet. If I remember right, it's dogs that can see further into infrared. And then obviously humans have technology that we can see further into ultraviolet or infrared with these various technologies. We use X-rays, which are quite a bit further or higher frequency, so closer wavelengths than violet, and then gamma rays even higher than that. You'll be familiar with radar and microwaves. So that is further to the left or to the red side of the spectrum. So it's even past that, even longer wavelengths. So yeah, we see this small area here though. So the structure of an eye, if you're familiar with a camera, if you've ever used, not just like your cell phone camera, although it does actually have a lot of these components in it. If you've used, say, like a professional kind of camera with a lens and a sensor, and you can detach the lenses, your eye actually functions quite similarly to those cameras. So there is the lens, and there is this aperture for letting in more or less light to have it brighter. You can also focus, move the lens front and back. And then there is a film at the back. And this is very similar to how your eye is structured. In your eye, you have the lens that the light passes through. You have the pupil that can open and close to be bigger and let in more light, or smaller and let in less light. And then here at the back, you have the receptor cells. The rods and cones are back here, kind of like the film of your eye, and that's where you're getting the light hitting, and then you are sending that from those receptor cells into the optic nerve, into the brain. So with that, any object you see is flipped upside down, so the light image is flipped upside down, but then your brain puts it back up. So the however you say this, is the white part, and that's basically the shape or structure of your eye. So that's the kind of round ball shape of our eye. The iris is the colored part, and it's a muscle, and that is adjusting the size of your pupil. So the colored part of your eye is a muscle. So I feel like there might be some flirting that could come from that about colors of eyes and muscles. So you figure it out, use it with someone that you're trying to flirt with. So that's very similar to the camera aperture that opens and closes. So the camera aperture kind of spins, spins like this to close down tighter or open up wider. Similarly, our muscles either pull the pupil open or let it relax closed. Then the pupil is where that light passes through and gets to the back of our eye. The cornea is the protective layer of the eye right here. So your contacts would be sitting on top of that, or my contacts, because I have really poor vision, are sitting on top of that. I guess you can wear contacts with not very poor vision. Some of my friends have contacts, and I'm like, I can't believe you even wear them because your vision's so good. I could not drive without my contacts, that's for sure, at least not safely. I don't know if I could even get out of my driveway without contacts. So the lens is very similar to a lens in a camera. It is a flexible disc-like structure that focuses the light. So you've got other muscles connected to that lens that help you focus the light, so you can focus on things further away, closer to you. A camera does that differently. You generally moves the lens a little bit further away or closer, but since our lens is flexible versus the lens of a camera would be glass, those work a little bit differently. All right, so here's that picture a little bigger. And let's zoom in to this area back here on the retina. So the retina is this light sensitive surface. This is where our rods and cones are. And this is where we pick up that light energy. So the rods are receptor cells that are sensitive to dim light, and they're not very useful for color vision. It's essentially giving you the sense of light and dark, and you can get shapes. So probably that image that we looked at earlier, the black and white one, could have been using a lot of rods and cones. So we have about 120 million rods in our eyes. So again, that's these red cells here. And then the cones are these more pinkish cells, and they're a little bit cone shaped. So we have about 6 million cones, and they are the receptor cells for color. So we have 120 million rods sensitive to bright and dim light, and then only 6 million for color vision. So we do have multiple different cones that are receptive to different wavelengths. So certain cones are receptive to certain wavelength spans, and we have a couple of those. And so what the optic nerve is, well, here are the rods and cones actually. So we're zooming in, here's the back of the eye. So this is actually the back of the eye right here. And interesting, us and other mammals have evolved so that our rods and cones are actually way back here. So the light passes through these other cells on the way to getting to the receptors, which I find fascinating that this is how we evolved, so that the light sensitive portion of our eye isn't actually the first thing that the light hits. It has to pass through these other cells. It always has made me wonder, like, if we evolved with it the other way, how much sharper would all animals' vision, well, at least mammals. I'm not sure about all other animals. I don't know if like insects' eyes are structured even close to similarly as this. But these are called, I don't want to get them mixed up actually. So we have, first we've got, I don't have it listed here. So we have ganglion cells and bipolar cells. Okay, the rods and cones, they're talking to the bipolar cells. That's these right here. And then these talk to ganglion cells, these yellow ones here. And then the ganglion cells' axons actually become the optic nerve. So the light itself has to pass through those ganglion cells, through the bipolar cells, through the cell bodies of these rods and cones to hit the light sensitive portions here at the ends, which I think is just fascinating. Well, the purpose of these ganglion cells, as well as the bipolar, or sorry, these ones, the blue ones, these are the bipolar cells, and then these ones are the ganglion cells, but they kind of do a similar thing. If you've ever taken a picture in RAW format, so you're getting every single pixel is saved. So your save file is going to be a lot bigger. Every single pixel from your camera is being saved as the color that it was receptive to. That's kind of like your rods and cones. Your rods and cones, they get the individual light frequency that they just received. So that's kind of like a RAW file. Then it's compressed a little bit. So it's compressed by these bipolar cells. So if all of these were seeing a blue frequency, then these two bipolar cells might just say about the same blue frequency. And then that is further compressed by the ganglion cells. So it's as if you're taking a RAW file down to like a JPEG. So what I just said might have made no sense except for the term JPEG. Essentially, you yourself, your nerves, are compressing the image you're seeing down to make it quicker to travel through your optic nerve and to your brain. And then your brain takes over that perception, that top-down process, and interprets what you're seeing. All right, so in the eye, we have a blind spot actually, right where this optic nerve is starting. all of the ganglion cells, all of their axons go together at that point and then goes out in the optic nerve. So every human has a blind spot in that one part of each of their eyes. With our two eyes, it never really bothers us because this eye will cover the blind spot for this eye. But you can actually see it if you use this little blind spot test. So hopefully your screen is big enough that you can see these two dots. So to find your blind spot, all you need to do is close one of your eyes and stare at the opposite color and move yourself backwards or forwards towards the screen. So if I wanted to test, what's this side? My right eye, I would if I wanted to test for the blind spot in my right eye, I would close my left. You might be seeing me backwards from what I'm doing. So I'm closing my left eye and I am looking at the dot on the left. So I'm closing my left eye, looking at the red dot. And then actually from where I'm sitting, the green dot disappears. So if I move a little closer, I can see it again. If I move quite a bit further away, I can see it again. But when I'm about the proper distance from my screen, I cannot see the green dot. And that's the blind spot of that eye. That's exactly where my optic nerve is. So there isn't any receptor cells right there in the optic nerve. And you can do the opposite. You can close your right eye and look at the green dot with your left eye, and then move backwards and forwards until the red dot disappears. So it's an interesting phenomenon. I think it's pretty neat. Go ahead and give it a try right now or later as well. If your screen is too small or anything, you can also do this with other objects. So try to see how big your, so Shay, depending on the size of your screen, like if you're watching on a phone, it's going to have to be really close to your face. My monitor is big enough that sitting, 3 feet back is about the right distance. But if you're on like a phone, you're going to have to bring it pretty close to be able to see that difference. You could also just use your fingers. You'll be able to see your finger. Well, you won't be able to see it disappear, but your fingertip will disappear if you do the same kind of thing. So you could hold up your right hand next to your right eye and close your right eye. Oh wait, wrong one. Which one am I trying to do? Yeah, okay. So hold up your right hand, say one finger near your, just like off to the side of one of your right eye. And then close your left. So my right eye is open, my finger is by my right eye, my left eye is closed, and then I'll slowly take my finger out. At a certain point, when you get maybe, maybe 1.5 feet, your fingertip will kind of get blurry and be gone. So right here for me is that point. So I'll try to turn this way. Hopefully I'm all in frame. Yeah, I'm entirely in frame. Okay, my fingertip right now is disappeared from my own vision from this eye. So it's about that distance. Hopefully that gives you a sense of where it is. Everybody has their optic nerve in about that same area. So play around with these dots. It might help if you just look at 2 dots, maybe smaller dots even, on a piece of paper. So you can just draw on, say, a normal size piece of paper, just draw 2 different dots and try that same pattern. So again, it's kind of off. So your optic nerve is kind of around, like off to this side. It's not directly in the middle of your vision. Directly in the middle of your vision is actually the fovea. And that is this space right here where we have a lot more cones in this little space. And that is the dead center of your vision, essentially. So that has a lot more color sensing cells right there and a lot more cells in general, because that is where your focus is. So when you're tracking words on a page, you're essentially keeping those words in your fovea. When you go from looking at your screen to, say, looking at your cat, you're moving your eyes so that the fovea hits on the cat directly. You do have other cells, other light sensitive cells right over here, but you can think of these as all belonging to your peripheral vision. And so there are fewer cells there, so your vision is actually a lot lower on your peripheral. You don't have, even with contacts, you don't have 20/20 vision on the things to your periphery because there's just fewer cells there. So you're getting a weaker message, less detail, things like that. All right, with that, with visual processing, we also have specific cells called feature detectors. So these are really specialized neurons in the visual system that respond to particular features of any given stimulus. So we have feature detectors like neurons that have trained themselves essentially to look for certain shapes, like be it a circle. There are definitely feature detectors for like ovals and circles and shapes for faces essentially. And for specific sizes, some feature detectors might look for big things versus small things. Other feature detectors are really responsive, so it's as if they get more and more active when you are seeing specific colors. And there's other feature detectors for movement. And so the brain learns to perceive these things through experience. We gain these feature detectors. Specific neurons will become a feature detector and look for essentially those specific things. So with that, our visual processing is parallel. So just like the right side of your body is being controlled by the left side of your brain, generally for people, essentially your left eye is going to the right side of your brain and your right eye is sending the message to the left side of your brain. And we use them both at the same time through a process called binding, and we put together the whole picture. So my right eye can't actually see all of my screen. So when I close my left eye, part of it's obscured by my big nose, essentially. But then when I open my left eye, I can see that part of my screen. So my eyes are working together to put that whole image together. So I see this bigger picture, essentially. All right, so let's talk about trichromatic color theory. And this is the idea that our color perception is produced by 3 different types of cones. One is red sensitive cones, one is blue sensitive cones, and one is green sensitive cones. So these are specific cones, like out of all these cones you see here, this one might be sensitive to red hues, this one might be sensitive to blue hues, and this one might be sensitive to green hues. So those specific wavelengths. And so I'll mention that in a minute, actually. So we have a lot of these 3 light sensitive cones in our eyes. So each of those pulls the information from that specific color and puts it to the brain as that color. So those red sensitive cones, they're sensitive to those wavelengths around red, blue sensitive to the wavelengths around blue, and green sensitive to those around green. So for people with red-green color blindness, if I'm not mistaken, it's their green cones that, for most who have red-green color blindness, usually it's their green cones that are acting up, either not functioning the same way or not sending the message. Usually for red-green color blindness, I believe it's the green cones that are acting up. So in these images here, this one should have the number 8 in this little circle, and this one on the right should have the number 5. If you don't see that 8 or the 5, or if they're a little hard to detect, it might be that you have a little bit or a lot of red-green color blindness. So with that, this is also part of what the ganglion and bipolar, when they pull different information from different cones and are compressing it down, it can also mix those colors. So if this cone and this cone are getting blue and a red, then the ganglion cell says, hey, let's put that together. This was actually a purple hue that both of these cones were seeing. So, so this is the most common color blindness is the green cones malfunctioning. So it makes it harder to distinguish that green from certain blues and from certain reds. So, all right, we also have other aspects of our visual perception. So this is the top-down processing, what our brain is looking for. So these are things that our brain is doing, putting the images together. We also can see things we see shapes. We pick out shapes. Our brain is really good at that. It learns to do that over the life course. So when we're born, we don't have we wouldn't notice that this, to me, looks like a triangle. Or this here looks like, I don't know, what is that? A horse, a unicorn, a rhino, something like that. Some sort of animal. So this is called the principle of proximity and closure. So I'm, in my own perception, closing this triangle to be a triangle, even though in reality it's this orange set of lines shape thing. I see it when I look, I identify, I perceive it as a triangle. Not necessarily that I'm filling this in, but if you ask me to identify that, I would say, oh, that's a triangle, not it's an orange shapy triangle-y thingy. So figure ground relationships is being able to pick up on what things are closer versus further away. So the size of my hands right now would be giving you a clue as to which hand is closer versus further away from the camera. So also depth perception. If you have two functioning eyes that are next to each other, it can give you the perception of depth because they're seeing things at a slightly different angle. You're essentially using your eyes to triangulate where the mug is. Is it really close? Is it further away? We can use the figure ground to do that a little bit, but the depth perception helps a lot more with that. All right, we also get clues from things that are familiar to us. So we generally know about the size of mugs. I know I've got a couple bigger mugs that are even like this big, but most mugs are generally around this size. So if I see in a picture or if I see in a scene a mug, I know it's probably about this size. And so I've learned that. I can kind of use that to perceive the rest of the picture. So this picture here on the slide, this is probably not a 3-foot tall paintbrush, right? This is probably a paintbrush that is just closer to the camera. You can also tell that because it's overlapping the person in the background, that the person is out of focus. So we use these clues to perceive the situation. It would be pretty funny if you saw that this was actually a giant paintbrush, and we've now perceived it this way. But it's almost certainly a paintbrush, a normal size paintbrush in a can or a glass jar, and then a human behind it. So with that, a newborn baby who's just now using their eyes to see anything other than just the light and dark that they could see towards the end of being in the womb, they're now seeing these things, these shapes, these overlaps, what a mug looks like. So they're developing those perceptions. And we're really good at building those. So after about age 2, we've got a lot of these clues in place. And our perception, our brain can interpret visual information pretty well at that point. Other things like the height in a field of view makes things seem further away. Generally things in a linear perspective, so those things smaller that are way down here look like further away humans than the ones up here. Shading, so the lightness or darkness of things. So you can probably tell there's some light sources in front of me based on the shadows here versus on the shadows that are hitting the wall behind me. Texture gradients, things we perceive things that are closer together as being further away. So it kind of looks like this is a slope and things over here are further away and these things here are closer to us, where in reality it's a 2D image and these things are in the same place on your screen. So we are really good at detecting motion. We have a lot of motion detecting neurons, and we attend to motion really well because of its survival value. So we oftentimes, these motion detecting neurons can get overexcited, you could say. So we might sometimes perceive something stationary as being in motion. And we'll look at an optical illusion in a minute that shows you that. It can happen in movies or with images. We're really good at perceiving things in motion, even if they are not actually in motion. Our brain wants to find those motion things to keep us safe. Perceptual constancy is an important part of our understanding of the world. We understand that even though we're seeing different images at a different time, it's probably not the objects themselves like morphing. It's that we have moved around them or something else has moved. So this person has probably turned their head in between these two pictures. It's not that they have their skeleton is somehow morphed and like facing off the other direction now. Seems like a good thing to happen in a horror movie, though. You see it's close to Halloween, and I've been watching horror movies. Is that clear to everybody? So yeah, so perceptual constancy, generally things in our environment stay about the same size, about the same shape. Cars are about the size of a car, so we can understand those. Rather than doing this, I think we'll get, maybe we'll do this. Because I do want to get to the optical illusions. I think those are fun. Well, if it's not going to load, then that definitely, yeah. This gives a couple other examples, but doesn't really say anything new from what we've talked about so far. It's kind of a review, and since we just finished talking about it, I don't think there's really any need to review it right now. So if you want to go back over and watch on, go for it. But let's talk about these illusions. So use whatever's the biggest screen that you can. So if you're on a phone, maybe hold your phone really close to your face, but don't hurt your eyes, please. Or if you're using multiple monitors, maybe put the illusions on the bigger monitor. It'll just make it easier for the illusions to work. So here, what you'll notice is that while this whole image is totally static, nothing is actually moving, it is just a flat image, it's not a video or a GIF or anything like that. As you move your eyes around, you'll see kind of a blinking effect. You will fill in these spaces except the one you're looking at. So right now I'm looking at this one and it's white, but now I'm looking at this one and this one up here was kind of gray. So as you look around at the different dots, you'll see blinking gray as your brain sees the similarity of the black and it's trying to fill in the picture, and so you're perceiving it this way. So the sensation is still always the same. You're still getting the accurate sensation of the squares of black, the lines of gray, and the circles of white. So that sensation is always coming in the same way, but your top-down processing as you're looking around the image is going to give you that blinking sensation. So here's an example of one where you may see movement where there is no movement. So again, this is not a GIF or a video in the slideshow at all, but your motion detecting neurons might be a little overactive and see some motion here. If you stare at it long enough, you might start to see things wave, or even the rings seem to rotate around, depending on how you're looking at it. Like if you try to make it go the other way, it might go the other way. So you might see this line rotating this way. You might see this line rotating this way. And then if you think about it, you might be able to make it rotate the other way. So for me, I don't often get the rotating effect. I see them as kind of like wiggling is usually how I see this one. So we are also using the perceptual cues of these lines. And so this line here probably seems shorter or less wide than this line right here, but they are actually the same pixel width. So this one and this one, I can't actually draw my mouse like straight down to prove this. Maybe I can make, nope, I can't make a line with it. But these are actually the same length. Now here is some patterns. So we will close these shapes because of their proximity and their similarity. Our perception will see things here. So what I see here is two different triangles. You might focus on the circles and maybe close up the circles, or you might see this as a Pac-Man eating a triangle or something like that. So you will create a pattern. Your perception will give you something about this. Fill in that gap. So this is better on a really good printed image or a really well calibrated monitor, because depending on your monitor, you might, or your phone screen, whatever it is, you might not get the effect quite as well. All of these yellow patches are identical, and depending on your monitor, it might be sending slightly different yellow. Like if your monitor is not great, this one might not be as yellow as this one. But as we look at it, they might appear different. So this yellow seems to me a little bit darker, a little bit dingier than this yellow here. This one seems really bright and vibrant to me. This one seems pretty bright and vibrant. These two seem the same to me. This one looks a little more dingy. This one looks not quite as dingy as this one, but more dingy than these. And then this one is interesting as well, similar to the line example. These orange circles here are also the same exact size. So here we've got the proximity to the large gray dots and the proximity to the small gray dots makes this one seem bigger than this one, even though they're actually the exact same size. So this is one of my favorites. So in this optical illusion here, we have the A and B. These are actually the exact same shade of gray. It's fine. So I'll flip through the picture in a couple different ways to kind of prove it to you, but these two different shades are actually the same shade of gray. So I'll show them connected here without a background. So you see here the A and B with that connecting road. You can now see they're the exact same, but when that connecting road is gone, even though they haven't changed, so if you stare at B and go between them, you'll see the shade stays the same. You stare at A, you'll see the shade stays the same there as well. Yeah, because of that shadow, it makes us perceive B as darker, or sorry, lighter than it actually is, even though it's exactly the same shade as this. All right, so there's our visual system. Let's take a quick break for about 5 minutes or so, and then come back and talk about the auditory system in not quite as much detail as the visual system, but definitely a lot of detail. So let's take a quick break till 3:57, and then we'll come back and talk about hearing. All right, and we're back. So let's talk about the auditory system and how it works, because I think maybe it's because I'm familiar with cameras, but the eye makes a lot of sense, those visual receptors taking in light, versus for hearing, the way that we hear things is through hair cells, and it's really quite a fascinating process, I think. So let's talk about hearing things. So the wavelengths of sound determines the sound's frequency, similar to the frequency of light, and we perceive it as pitch, whether it's a high note or a low note. So a high note would have a lot tighter wavelength. These wavelengths aren't actually that much different here, but a lot tighter wavelength than a low note would have a very long wavelength. So some wavelengths are too high or too low for humans. So a lot of other animals can hear different frequencies that we cannot. Similar to sight, other animals can see either ultraviolet or infrared. Other animals can hear higher or lower tones than humans can. So amplitude, or the height of the wave, we perceive as the loudness of the wave. So this happens because the air pressure, the sound moving through the air molecules, is pressing more forcibly against our eardrum when it's loud. So, and there's a lot less movement of that in eardrum. It's a lot softer movement when it's a soft sound, like, say, a whisper. Yeah. So the timbre is the fact that most sounds have multiple wavelengths. It's more mixed, like this image down here. And with that, we hear that as the tone saturation or the quality of the sound. If it's really clean or clear note, it's hard to put it in words. But if it's a single note that's really clear, versus if it's kind of mixed with other things or other sounds. So let's talk about the structure of the ear. So sound comes in through our ear canal. Our ear is actually shaped pretty well as a funnel of sound, kind of generally in front of us. So we can hear things behind us as well, but we can't pinpoint them quite as accurately as the things that are kind of around in front of us. So it funnels the sound down into the ear canal, and then that goes then to the eardrum. So this is the outer ear, this is the middle ear and inner ear. So here at the eardrum, it's connected to these couple bones. Hopefully you already read about this in the chapter. They're very tiny bones, the hammer, anvil, and stirrup. And then that's connected to the cochlea and these other fluid-filled canals. So these ones here in the cochlea are related to our hearing, our sense of hearing. The high notes, I think, are down in this bigger area. The low notes we hear up here. We'll watch a video and make sure I'm right on that. Sometimes I get them flipped around. And then these semicircular canals, they also have hair cells, but these are used for balance, for knowing what position our head is in. That can then tell us, like, are we doing a backflip, or are we swimming up or down, things like that. And then here is the auditory nerve, bringing in the information both from hearing as well as from our sense of place and position. So let's watch this in class, and it will talk about these systems and how they work together to then get the mechanoreception of those hair cells to enable us to hear things.
The sense of hearing is accomplished by a process known as auditory transduction.
The ear converts sound waves in the air into electrical impulses, which can be interpreted by the brain. As sound enters the ear, it passes through the external auditory canal, where it meets the tympanic membrane. The tympanic membrane then vibrates in response to the sound. Sounds of a lower pitch, or frequency, produce a slower rate of vibration, and sounds of lower volume, or amplitude, produce a less dramatic vibration. Higher frequency sounds produce faster vibrations. The tympanic membrane is cone-shaped and articulates with a chain of 3 bones called the auditory ossicles. They consist of the malleus, the incus, and the stapes. The movements of the tympanic membrane vibrate the ossicles, passing on the information of frequency and amplitude. The 3 bones pivot together on an axis shown here in red. The pivotal axis is due to a series of ligaments which hold the bones in place within the middle ear cavity. The anterior malleal ligament and the posterior incutal ligament are of particular importance for the pivotal axis. 2 structures which normally obscure this view of the middle ear have been removed. They are the chordae tympani nerve and the tendon of the tensor tympani muscle. Through the ossicles, the vibrations of the tympanic membrane are transferred to the footplate of the stapes. The stapes moves with a piston-like action, which sends vibrations into a structure called the bony labyrinth. The labyrinth is filled with a fluid called perilymph. If it were a completely closed and inflexible system, the movement of the stapes would be unable to displace the perilymph, and therefore unable to send vibrations into the bony structure. Due to the flexibility of a membrane called the round window, the stapes movement can displace the perilymph, allowing vibrations to enter the labyrinth. The corridor leading to the round window is found within the spiral portion of the bony labyrinth, known as...
So, a little bit off topic, but I think interesting, is that this structure, as well as the structure of the bones in our ears, is actually a really unique thing to mammals. So one of the things that makes mammals mammals, or that scientists use to determine if an animal is a mammal, is hair, but also the inner ear structure. So if they have this similar kind of inner ear structure, they need the hair and the inner ear structure to be determined as a mammal, which I think is interesting. I only learned that recently, like within the last couple of years, so kind of neat. So other animals outside of mammals have a very different way of auditory getting these receptors for hearing. Similar in some ways, but different enough that the structures look very different for them.
The cochlea. Vibrations produced by the stapes are drawn into the spiral system and return to meet the round window. The portion of the spiral passage in which vibrations ascend to the apex of the cochlea is called the scala vestibuli. The descending portion of the passage is called the scala tympani. A third structure, called the cochlear duct, is situated between the scala vestibuli and the scala tympani. The cochlear duct is filled with a fluid called endolymph, and when viewed in cross-section, the membranes separating the 2 fluid-filled systems are visible. They are Reissner's membrane and the basilar membrane.
So all the specificity about all the membranes, you don't have to know in that much detail for the exam, but I do think it's good to know a little bit more to understand the portion that is important for us for the hair cells and how they're actually hearing. Because here is where the hair cells actually are, right here, and it's about to zoom into that. So you'll see it. They're very, very small. They're literally individual cells, and it's because of the motion of these fluids and essentially this flap touching the hair cells that we can hear.
The membranes are flexible and move in response to the vibrations traveling up the scala vestibuli. The movements of the membranes then send vibrations back down to the scala tympani. A specialized structure called the organ of Corti is situated on the basilar membrane. As the basilar membrane vibrates, the organ of Corti is stimulated, which sends nerve impulses to the brain via the cochlear nerve. The actual nerve impulses are generated by specialized cells within the organ of Corti called hair cells. The hair cells are closely covered by a structure called the tectorial membrane. As the basilar membrane vibrates, the tiny clusters of hairs are bent against the tectorial membrane, triggering the hair cells to fire. The entire basilar membrane does not vibrate simultaneously, triggering the hair cells to fire.
So this is the process by which our hair cells enable us to hear. It's because of the vibration around it, moving this membrane, and literally touching the hair cells. And that is where we get our sensation that then goes to our brain, and then we perceive as hearing, whether it be language or music or a tone or a siren. It's because of this mechanoreception. So again, hearing is done by mechanoreception, is done by that physical touch between those hair cells and this membrane there.
The entire basilar membrane does not vibrate simultaneously. Instead, specific areas along the basilar membrane move variably in response to different frequencies of sound. Lower frequencies vibrate the basilar membrane closer to the apex of the cochlea, whereas higher frequencies produce vibrations closer to the base. This arrangement is known as tonotopic organization.
That in another way, in case it was unclear, this upper part of the cochlea, of the membrane within that cochlea, so the more center part of that snail looking thing, is where we hear low tones. So this lower tone versus a little bit higher tone is heard in this part of the cochlea versus this part of the cochlea. So with that, we tend to lose the hair cells down here at the more base part of the higher tones first. So we lose those high tones first earlier on in life. So if you're about 20 or 21, you are already starting to lose some of the hair cells that you once had. So if you're 18 or 19, there's some high tones that you can probably hear that those of us who are older than 21 probably cannot. So it's interesting.
Together, this sequence of events is responsible for our acoustic perception of the world around us.
So pretty interesting process by which we can hear things. Very different than I assumed it would have been before learning about it. Light is received by light sensitive cells, but for hearing, we have these hair cells that, because of the vibration of the air pressure or of the air and then hitting that eardrum, moving those bones, then vibrating a specific part within that cochlea, we have those hair cells that are activated by being touched by that membrane, and we can hear a tone. So interesting. So with that, here are some of those pictures that we've seen, and then a close-up of this organ of Corti with the hair cells. So you can see here it's similar again to other neurons in that this receptor gets a signal here from being touched or pushed or vibrated, and then it sends it past its cell body down the axon. These connect together into our auditory nerve. So, and then similar to other places in, there are other cells supporting these cells and things like that. All right. So with that, hearing loss happens in a couple different ways. One that I just mentioned was that most people lose hearing of our high tones because of damage to specific hair cells or locations in the cochlea. So you can look for hearing tests online, and depending on how good your speakers are or your earpieces, you'll be able to listen to see how low of a frequency or how high of a frequency you can hear. Someone who is under 20 will tend to be able to hear more higher frequencies than someone who's over 20. And it kind of just keeps not consistently. There's kind of a stopping point or a plateau. And then once we get closer to 50, 60, 70, and then 80, then there's a bigger drop as we get closer to 80 of hair cell damage. So with that, cochlear implants, though, work in a slightly different way than hearing aids. Hearing aids are basically a little speaker that you put into your ear, and it amplifies the sound at the same wavelengths. Cochlear implants are very different. So they have a sound processor that they then transmit inside the skull, essentially, into this cochlea, where there are literally parts of wires that are stimulating individual auditory nerves. So they're stimulating hair cells specifically rather than amplifying sound in any way. So that's what a cochlear implant does. It's implanted into the cochlea to then activate specific hair cells or sections of hair cells. So it helps any of the working auditory nerves work properly, get the message properly. So pretty neat. So the place theory of pitch perception was talked about in that video. Essentially, that different places on the cochlea correspond to different pitches. So those closer to the center of the cochlea, those are low notes, versus towards the base or the broader part of the cochlea are the high notes. Oh, with this also, the volley principle means with any nerve, and this is quite quick, any nerve can only fire up to 1,000 times a second, which is quite fast. So that's essentially the limit of the process to bring those sodium and potassium ions back and forth across that membrane. So it's limited to happening 1,000 times a second. So what the volley principle is essentially that if there is an even louder noise or an even brighter light or an even more intense feeling of like pressure or pain on your hand, your perception can then take all of those inputs and give you a perception of having more pain or more light or more sound than your nerves can actually send you, which is an interesting thing about our perception. So touch, we've talked about the part of our brain. So the somatosensory area is right next to the motor cortex. There's a longer name for it, but it left me. So this is why notes are good when taking an exam. Even if you think you know something, sometimes it just leaves your brain, right? So most of our receptors for touch are in our skin, though we do also have some of these touch sensors or touch sensitive cells in our muscles and other tissues too. So these messages go through the spinal cord to the thalamus and then to opposite sides of the brain. So me pinching or flicking my fingers on my right hand are sending that message to about right here on the left side of my brain. For temperature, we have other specific neurons that are called thermoreceptors. Their primary purpose is to make sure that we're staying at about 98.6 degrees so that all our body processes run appropriately. So we've got these thermoreceptors, and they're sensitive to the temperature. We've got these corpuscles that are sensitive to touch, and then pressure for these. And these can be in other organs like the fat beneath our skin, or even in muscles as well. So altogether, they can give us a lot of different sensations. The sensation of poking versus like rubbing your arm versus something cold on your arm. All of these are received and interpreted in different ways from these couple different receptor cells. Oops. So for pain, this is an interesting thing, is that, well, I think it's interesting. Hopefully you find it interesting too. So the same sensors for touch are the ones that send pain signals. Similar to how we have that absolute threshold of the minimum level to have the neuron fire, there is a certain threshold in these receptors that rather than now sending a sense, will then send a sense of pain. So if it's getting enough energy, then it will, when it crosses that threshold, it now sends a pain message. So it's the same exact ones that are detecting touch that will send the pain signals. So even light or intense spice, or oh, I see. I've cut off some of the letters. Even light or an intense spice on the tongue can trigger pain as well. So you can get pain in your eyes, and again, that's still just the rods and cones sending the signal that they're getting overloaded with this. They're going past their threshold to a point where it says, hey, now we're feeling pain. We also have receptors, different kinds of receptors in different organs in our body, as well as muscles, and those generally aren't apparent to us, but our hypothalamus is keeping track of those. It's related to the hormones and the endocrine system, and so it keeps track of what essentially organs are doing. So with those, we can feel our organs intake in certain cases, but to be conscious of that perception, it generally is a really high absolute threshold for us to be aware of those sensations. So for taste, we have taste buds. Our taste buds are sensitive only to salty, sour, bitter, sweet, and umami. And so umami is essentially MSG is activating that umami receptor. So it's really good. You can get cans of MSG. Some people are allergic, so maybe don't just like run out and get MSG, but it's naturally in cheeses, meats, things like that. So smell helps us detect rotten food and keeps us safe. That's evolutionarily one of the main reasons for it. It might help even in humans with mate selection by detecting hormones and finding mates with different enough genes that it would be beneficial to the species to mate with. So this is really clearly the case in a lot of different animals, rats, for example, but it's not as clear in humans. So there have been, you can maybe even do a question paper on this. There have been studies where different people are given smells of people of the same and opposite sex, essentially samples of sweat on, say, t-shirts or cloths, and asked to say, like, if they find that person attractive or not attractive based on these smells. And so these are essentially trying to see if we as humans can detect these kinds of hormones. And so some of these studies do find positive results that, yes, humans can detect hormones on average, but then there are other studies that show that no, humans aren't good at this process. So it's still a little up in the air there. Do humans use smell to detect mates? Maybe. So yeah, it's interesting though. it would be, I think it would be a little strange if we had completely lost that ability at this point in our evolution. It's pretty clear that it's not as strong of a sense and perception as it is in, say, rats. All right, so we also have this kinesthetic sense, the sense of where our body is within space. If you have ever tried dancing or doing something like parkour or gymnastics, you've tried to use this kinesthetic sense a lot. Even just doing something like picking up your water bottle uses your kinesthetic sense. These are neurons or receptor cells that are in your muscles and your tendons that help tell your brain where your body is in relation to itself. So even if I close my eyes, I mean, I'm intentionally choosing to do this, but let's say you wake up. And it's really dark. You can't actually see where any of your body is. You would probably still be able to feel that, say, your arm is next to your head, or that one of your arms is like off on the side of the bed. Like you still know where your limbs are. This gives us a lot of feedback and helps us do things around the world, or in our world is what I'm trying to say. The vestibular sense is using the other part of the ear. So these semicircular canals, they're also filled with that same fluid. They're also filled with cells very similar to the hair cells we use for hearing. But we get from these if we are on balance, if we're tipped over, if we're moving backwards, forwards, if we're accelerating. So that is what these sensations tell us. So that is the end of chapter 3 slides. These are essentially just extra slides here that I can use to put in extra stuff. So that was a lot faster than it generally is through chapter 3. I feel like I might have skipped something, but I think we went through everything. We did skip that one video, but that was just kind of a review on visual perception. Yeah. I mean, chapter 3 is a little shorter, but we did go through a little bit faster than I thought. So with this extra time, I will pull up the study guide. Hopefully, you've been looking at the study guide already. So there's the actual exam right there. So are there any questions from anybody on this study guide? So hopefully some of you have looked it over a little bit by now. Since we have the time, I could go over a couple answers that anyone was confused on. We literally just talked about this. Abel knows that his legs are crossed and that his hands are on top of his head. This is a demonstration of... Put in the comments what the correct answer is, A, B, C, or D. All right, we've got 2 responses. That's better than none. Maybe some others are coming in, but yes, it's D. The answer here is D. So that is proprioceptive feedback. And so that comes from those neurons and those receptor cells that are in your muscles and in your tendons. That's how you know that your hands are maybe on top of your head, or if you wake up in the dark, that your hand is near your head and another is off on the side of the bed. Those kinds of things. This is something we talked about today as well. Jane is having trouble sleeping as she sits on her bed looking around the dark room. She notices that her peripheral vision, so that's the vision on the outside of the fovea, seems to be better than her central vision. This is because vision in low light conditions, either A, B, C, or D. So what does low light vision depend on? It's obviously not C, right? We're using our pupil all the time because that's what light's coming through, right? And light definitely does require the retina because that's where our receptor cells are. So it's down to A and B, the rods or cones. Which ones have to do with visibility in low light conditions? So I see a couple B's and A. So low light would be using mostly our rods, so rather than the cones. So the cones, again, they're the ones for color vision, and they need a lot higher intensity light. The rods work on lower intensity light and don't have color vision, and there are more rods in peripheral vision, and there's a lot more cones in your fovea. So here I'm going to go back to the eye. So here we've got the rods are the more column looking cells and the cones are the more conical looking cells here. So again, rods, we've got more of those in our eyes, about 120 million. And then cones, we've got only about 6 million. So the cones are for color vision and they do need a higher intensity light. So essentially the cones' absolute threshold is higher. They need more energy to be able to see the color. This is why when you're in a really dark room, it's hard to perceive colors of things. It's more like your vision is more black and white. So being in a dark room, noticing that your peripheral vision is a little clearer than your central vision, it's because your central fovea has a lot of cones versus the peripheral vision has a lot of rods. So it's the answer to 13 here is A, depends on the rods. So talked about synapses and action potentials. Types of psychology, we've talked about that a couple times. See if there's another one. It's really related to what we talked about today. Most of these are, the open-ended questions are from chapters 1 and 2. So generally the exams tend to be about evenly spaced between the different chapters. But you could kind of tell probably, since we took more time on chapters 1 and 2 than chapter 3, there's a few more questions on chapters 1 and 2 than there are for 3, but they are pretty evenly split. I don't have an actual number breakdown. That's just how I try to write the tests, is so that each of the chapters is about equally represented. So are there questions when looking through this study guide that you want to cover? Again, all of the questions on the exam are similar to those that you see 7, 8 through 14. Multiple choice, if it's true and false, there's 2 choices, obviously. But generally, multiple choice for possible answers. Some of them might be completely ridiculous answers, like does not require use of the pupil. Some of them might be a little tricky, like what are cones versus rods? Can be a little tricky. That's a good question. More like what you'll see here in the study guide. So by homework assignments, I'm assuming you're meaning the Smart Book quizzes that you do as you're going through the book. Okay, yeah, so the exams will be more similar to these couple questions, 7 through 14, than the questions that are covered in the Smart Books. The Smart Book sometimes asks questions that are not on the test, but I try to focus it down. So yeah, essentially the way the Smart Books work is it's possible that it could ask you questions about every single paragraph in the whole Smart Book, and I try to get it to focus, but I don't have like a infinite control of the Smart Book, so I try to get it focusing on the topics at hand. But sometimes it does ask you questions in the Smart Books that aren't on the exam, and the way that it asks questions are often like with an open-ended answer or like a fill-in-the-blank kind of thing. So it won't be like that, but it will generally cover the same kinds of topics. But this is the format of the questions from 7 through 14. So really good question. Hopefully that helps everybody prepare and feel a lot more comfortable when the exam opens tomorrow. I find students are most concerned and nervous before the first exam. Yeah, you're welcome. So again, these questions here, you'll find a few questions on the exam concerning these topics, and then you'll find some of these questions word for word from 7 through 14 in the exam, or slightly different on the same topic. All right, well, if there's not any other questions, if you do go through the study guide and you're really confused about something, you wonder, oh, what is a theory? What are the functions of a theory? Feel free to email me. For that one, I might actually just point you to the section of the lecture recording to go over that, because that was kind of a big discussion. So, but yeah, let me know if you have questions. I won't be giving a whole answer key on the study guide. Oh, good. We do have a question, not about the exam, but question papers. Yeah, definitely send me a question or two regarding the study guide if you have them before the test. It's better to get them today or say tomorrow morning rather than I probably won't be looking at my email at like 5 o'clock on Saturday afternoon. Actually, I'm sure I won't be. That's Halloween, so my favorite holiday. So definitely get those questions in earlier rather than later. So a question with regards to the question papers, the first one needs to be about something we've discussed in the first unit, either the first or second unit. So the first question paper is due when the second exam opens. And so it needs to be about either chapters 1 or something that we've touched on in lecture or in the books, chapters 1, 2, 3, 4, 8, or 11. So 4 is, we just did sensation and perception. So 4 is consciousness, dreaming, sleep, hypnosis. 8 is developmental psychology. 11 is social psychology. So somewhere around those topics should be what the first question paper should be around. Yeah, it could be connected to more medical related material than exclusively psychology, but it should be pretty related to what we've talked about in class. So great question. All right, well, thank you for your participation today, and I will wish you good luck on that exam. Again, it's open tomorrow till Saturday night. So have a good and safe Halloween and enjoy yourselves.